much for having me here. I'm a postdoc at the CFA. I'm currently looking at a sample of quadruply lens quasars that don't have Chandra observations. But today I'll be talking about how we can use AXIS to probe fundamental physics. Just one second. Okay, so yeah, my argument will be that AXIS will allow us to test an array of well-motivated models beyond the standard model of particle physics. So AXIS will be able to help us test or understand something about the nature of dark matter and also string theory. And of course, if you haven't been speaking to your cosmology friends too much, I would like to draw your attention to the fact that the recent results from the dark energy spectroscopic instruments combined with CMB as well as supernovae results are sort of hinting or suggesting that we might be living in a universe where the dark energy equation of state parameter has a non-constant component. And if lambda CDM and the way we have been parameterizing it is correct, we should be living in this region of parameter space. And this is what seems to be currently disfavored by these three observations together. So this is one of the key motivations as to why we want to use or look at physics beyond the standard model theories. So what I'll be discussing, as Eileen said, is the implications that AXIS will have to study axions, in particular very light ones. And I'll also try to mention the possible implications for looking at KV scale dark matter particles. And the axion results that I'll be mentioning for AXIS and NewAthena were published in 2023. So please bear in mind that these quantities or these numerical results were inferred with the responses and the observatory specifications that were available at the time. And finally, I want to highlight that our GEO proposal that is part of the AGN science case also relates to how AXIS will be able to help us constrain dark photons as and primordial black holes. Okay, so why do we care about axions? So you may know that the first type of axion that was introduced is the quantum chromodynamics or QCD axion. And this particle was introduced in the 1970s, and it was famously named after a detergent. And sorry if you have seen this image many times, but it really sticks to your mind. And this is because this particle was proposed to clean up one of the problems of the standard model of particle physics, and this is the strong CP problem. This is the absence of charge parity violation that we see in the strong nuclear force that we see in nature that clashes with the predictions of the theory. Secondly, you may know that in 1983, there were 3 independent groups that showed and proposed that this QCD axion that solves the strong CP problem can make up the entirety of the dark matter in the universe. So if this is the case, the axion will have masses of tens to hundreds of micro electron volts. So this is 9 orders of magnitude, approximately less than the mass of the electron. And you may also know about the more generic class of ultralight bosons, where axions here would be a fuzzy dark matter particle of mass of 10 to the minus 22 eV, and this corresponds to a de Broglie wavelength of a kiloparsec or so. So this is the sort of halo size for a dwarf galaxy. But the type of axions that we'll be talking about are more generically called axion-like particles. So these do not solve the strong CP problem in particle physics, but they are ubiquitous in many theories extending beyond the standard model, such as string theories. And these particles are characterized by 2 parameters, so the axion mass and GA gamma, which is the coupling strength of these light axions to electromagnetism or to photons. And you can think of this as a cross-section strength. Okay, so how can we use astrophysics to probe axions or to try to detect axions? So we can do this generally in two ways. So we can produce them in the presence of large radiation fields, and this is a case for stellar cores. And I'll show an example in the next slide. But we think of photons interacting with ions, for instance, and then producing axions. And then secondly, we can also have photons interacting with external magnetic fields and then producing axions. And we refer to this as photon axion mixing. So what we want to think about, given that these interaction is triggered in the presence of these external magnetic fields, we want to think of photons that are produced in the universe and are interacting with cosmic magnetic fields. And if we're in a suitable location of parameter space, then these photons will undergo conversion into axions. So we can think analogously to neutrino flavor oscillations, where we have a neutrino interacting with the atmosphere and having a non-zero probability of mixing into a different neutrino flavor. But here we have photons shining through magnetic fields and then mixing into axions. So what does this probability look like? So for a given very simple magnetic field geometry of this medium, what we have is that this probability is an oscillatory function with the energy. It's energy dependent, and the amplitude increases with the energy. But for a given energy, we also have oscillations with the path length traveled by the photons before they mix into axions. And in this specific case, this path length corresponds to the coherence length of the magnetic field. So this is just an example of how we can use astrophysics and environments that you might be interested in to constrain axions. So Kirsten Perez et al. Used new star observations of Betelgeuse to constrain axions. And the thinking here is that axions are produced in the stellar core, and then they have a non-zero probability of mixing into X-ray photons as these axions that escape the stellar surface interact with the galactic magnetic field. Then Christopher Desert and Bushman et al. Used Chandra observations of the Magnificent Seven, which are 7 isolator neutron stars, to probe axions. And here the thinking is that you can get axions produced at the core of the star, and then once they reach the magnetosphere around the neutron star, you might be able to resonantly produce X-ray photons. But the type of environments that I'll be talking about are clusters of galaxies that are hosting AGN. So we have seen this image from the Perseus cluster a few times already. So the thinking here is that we have an AGN that is sitting at the center of a galaxy cluster. The cluster is permeated by the ICM, which is magnetized. So as the X-ray emission from the AGN interacts with the magnetic field of the cluster, then we might expect some of these photons to undergo conversion into axions. So if this happens, we'll see spectral distortions in the spectrum of these AGN that are somehow related to the magnetic field in the cluster. And I'm happy to describe this later. But here's an example of what we might expect for the Perseus cluster of galaxies. So we see that the amplitude of this signal, which I've quoted here as 1 minus a mixing probability, has an amplitude that corresponds to a few percent. And we see that these energy distortions are very fine in energy space at low energies. Okay, so I'll be now moving on to the current best constraints that we've been able to set on these light axions that I've mentioned are predicted by string theories. And what I want to highlight is that the fact that what we want to do again is to look at the X-ray spectra of these AGN. So if we don't see these distortions, then this means we can constrain axions. So the current best constraints come from Chandra grating observations of H1821. So H1821 is an extremely luminous quasar that is hosted by a galaxy cluster. It's a relaxed cluster at redshift 0.3. And here on the right-hand side, you see the on the upper panel, you see the best fit model to the Chandra gratings data. So each color represents a different data set out of 570 kiloseconds. And the use of the gratings here is really important because it allows a very high quality extraction of the intrinsic emission from the quasar, free from cluster contamination. And here on the lower panel, you see the residuals resulting from fitting this data with the best fit astrophysics model. So given what we know about type 1 AGN. So what we wanted to ask ourselves is whether photon axion distortions are responsible for these structure that we see here. And the answer is no. And I'm very happy to go into the detail of how we came to this conclusion. But what I want to highlight is that with this data, we found no evidence for these light axions. So we were able to set these bounds on these low mass particles. So here what you're seeing are upper bounds on G. So this photon axion coupling constant for a given axion mass. And these are our results from H1821. So you see that these were able to improve from previous bounds that were set with Chandra observations of NGC 1275, which is the central AGN in the Perseus cluster of galaxies, as well as M87 and Hydra, so the AGN in the Hydra A cluster that was mentioned in one of the previous talks. And the implications of this is the following. So here on the right-hand side, what you see are predictions for this G effective, which is related to this coupling strength parameter that we're constraining for different string theories. So each theory is represented by, the predictions of each theory here is represented by a different color. And here, what changes in each of these theories are the number of axions that your string theory predicts. So you see that our current bounds, best bounds with Chandra, are in tension with string theory predictions that feature a large number of axions. So this is potentially very exciting because it suggests that X-ray astronomy may be able to help us constrain some of these string theory predictions and even inform some calculations that will be performed in the near future. Okay, so the relevance for axis is what you see on the right-hand side. So these are projections on axions in the same mass range that we saw before for a 200 kilosecond axis observations of NGC 1275. So again, this is the central AGN in the Perseus cluster, and these were inferred by simulating an axis exposure to NGC 1275, and then seeing whether we would find evidence for axion distortions in the spectrum. And the answer is no. So with this, we were able to place these projected constraints. And clearly, you see that these are able to improve on the current best bounds that we have from Chandra by a factor of 3. And this is really driven by Axis's collecting area and the improvement in collecting area with respect to Chandra. And another important consideration is the spatial resolution here, because when we run our simulations, and you can see that here we also reported results for Athena, the important thing is for the axis simulations, we didn't have to take into account the ICM emission. So this is something that really drives these results too. I'm probably going to stop here and take questions, but what I want to highlight, and hopefully I've convinced you about, is that there's mounting evidence for the need of physics beyond the standard model, and Axis will help us probe an array of string theory and dark matter models. Happy to talk about this. I'm thinking about KV scale dark matter, and there are many open research directions that remain unexplored, and I think it's a good thing to think about whenever you're presented with high quality data. You might want to think about how you can use this data to address the astrophysics question that you're most interested in, but also think about possible implications for studying axions and other models. Thank you.
Okay, we have multiple questions, so I'll start with Vanessa.
Okay.
Hey, so Julia, I was wondering what happens if you have a more refined model for the magnetic field. For example, if you were to have like an MHD model for the cluster or so, what would be the difference in your results in modeling?
Yeah, so I mean, thank you, Vanessa, for the question. Maybe I will start by clarifying what we assume for the how we actually build this magnetic field model. So what we do is to split the cluster line of sight into boxes. And we basically, this reproduces the range of coherence lengths that we know clusters of galaxies have from Faraday rotation measures. And what we do is to assume that the magnetic field is independent and random. The direction of the magnetic field is set randomly and independently from one box to another. And what we do is to solve the equations for photon axion mixing. So this is essentially a linear algebra problem from in this box, and then we use the output, so the solution, as the input for the next box. And we do this concurrently and recursively up to distances of 1.5 megaparsecs or so. So these are so-called cell-based models for the magnetic field. And of course, we don't know what the direction is. And the direction matters because we get only photon axion mixing as we get a perpendicular component of the magnetic field that is non-zero relative to the line of sight. And this comes from the particle physics, Lagrangians and stuff. So what we do is to build like hundreds of realizations of this magnetic field structure where we're trying to model the turbulent structure of the field. And then we fit it all. We make axion predictions for a given set of parameters for each of these realizations. We fit each of these models to the data, and then we marginalize over realizations. But we suspect that, there's some work that has been done in using MHD simulations of turbulent environments, not necessarily clusters, but externally driven turbulence in a 200 kiloparsecs box that shows that the photon axion mixing signal increases or is stronger at hard X-ray energies compared to the predictions of these magnetic field, simple magnetic field models. So what we want to do in the next step is to make these calculations and these predictions for a more realistic MHD cluster environment. And then another step beyond that would be to use the predictions from the MHD cluster simulation to actually fit it to the data. So sorry, that was very long, but I think it's important to, it's the next step, so.
Okay, maybe one more quick question if anybody has one. Okay, I will just ask something really quickly. Is there anything to be gained? I'm used to thinking of dark matter searches from the gamma ray side. So is there anything to be gained from like a multi-wavelength sort of mode here, or?
Yeah, so I mean, very good question. My answer is that I don't know exactly, but in general, we think of different wavelengths as something that allows you to probe different masses.
Yes,
so if I go here, like NGC 1275 has been used both in the X-ray and gamma ray band to constrain axions, and the gamma rays allow you to constrain like 10 to the minus 9 and masses below, and the X-ray 10 to the minus 12 and below that. But it's a good question.
No, that's good. They're complementary, so it's like they're not duplicates. They're separate ranges. Yeah, that's good.
Yeah, and the X-ray is the part of parameter space that really allows us to set the tightest constraints on gamma for these lower masses. Yeah.
Cool. Very good. All right. Thank you. I think we have our next speaker up, Esra Bulbul. Oh, right. Yes. Yeah. You should get the microphone. Move this thing. I guess there's no way to move this, right?
I would, maybe just put it in the bottom corner.
Oh, yeah. Let's see if we can. That's better.
Yeah, the other stuff will. Show,
Okay, there we go. All right. Is that the end? Oh, it keeps doing that. Oh,
Feels like it's stuck.
there we go. Okay. All right. So next we have Esra Bulbul, who'll tell us about tracing the cosmic web with Axis and eROSITA. Thank you.
Thank you. So it's a great pleasure to be talking about large-scale structure with the eyes of eROSITA today here with you. And I would like to take you to a little journey where we can also see where Axis can contribute to the science. And of course, I give this presentation on behalf of my working group here. So now we're going to be talking about really large scales. In this presentation, I would like you to take a little bit of a step back and look at the universe from very, very far away. So what you're seeing here are the dark matter particles, and we are looking at the universe from a distance, and all these structures basically traces the large-scale structure in the universe. This web-like structure is called cosmic web, and where they meet, what we call nodes, are where the clusters of galaxies are located. So if you zoom into one of these clusters of galaxies and look with a perfect X-ray telescope, this would be an image you would see. Here you have no background, no PSF issues, no nothing, right? So these are projected X-ray intensity from illustrious TNG observations. So in cluster jargon, we talk about the boundaries of large-scale structures. So virial radius is around R200M, which is marked in that dashed line there. And then you can see these clusters of galaxies, in fact, are fed by the surrounding filamentary structures. The filament emission, this is the diffuse emission that you see in this picture, but you also see some bright low mass halos falling onto these clusters and having these clusters grow. And then the empty spaces mark where the cosmic voids are, right? So that voids are filled with very cold gas. And then when the cluster's gas basically meets with the void, it gets shocked. And then you basically can observe these features called accretion shocks. But what we're going to be talking about today is the emission in the very outskirts of clusters of galaxies and even the gas in the filaments. And we will be going way out from 1 megaparsec, which is now possible through current observations, all the way out to 5 megaparsecs. So if you just look at the 3D profiles from illustrious TNG simulations and look at the temperature of clusters of galaxies in two directions, in filamentary direction or void direction, you can basically see this temperature drop in the void direction, which marks the accretion shock. And you can see the same feature in the entropy profiles. And if you look at the number density profile of the hottest gas that we would observe in clusters, you can also see the shocked gas in the void direction around basically 2 to 3 R200M. R200M, as I said, it was a virial radius, and it's basically defined as the radius where the number density of the gas is 200 times the mean density of the universe. So this is way beyond the critical density of the universe. So if you just look at basically the surface brightness of the X-ray gas, right, from cluster outskirts all the way to the virial radius, the inner part of clusters of galaxies can be modeled with simple models like Wiklinen model, which are built from Chandra observations, and they can represent our understanding of the gas around this radius, basically shown in the white arrow here. But beyond that, we don't really know what is happening to that gas. In the simulations, beyond that radius, you can see there's some flattening because of the filamentary gas, but then there are some spikes. Those are the infalling halos. Right now, basically, we cannot explore that region beyond 1 to 1.5 megaparsec and beyond with Chandra or XMM Newton because we don't have sensitivity. So these are the state-of-the-art observations. Suzaku was great in that regard because it had a low particle background, and so several groups looked at the nearby clusters in different arms and were able to map the gas from center to the outskirts, and they can go out to R200C, which is R200C is way below R200M. Right, so these are the state-of-the-art observations. And here we come to eROSITA. eROSITA is another soft X-ray telescope, right? So it has a ginormous sensitivity in the soft band, and that makes it very sensitive to faint cluster outskirts. We have collected data about 2.5 years before we put the eROSITA in a safe mode. So we had our fair share of drama on the other side of Atlantic. But we have now in the eROSITA archive 42,000 clusters of galaxies. You have seen only 10,000 of them in the literature. We are hiding a little bit more than 42,000 at the moment. And those data will become public in 2028. But what we can do now, we can stack the data, right? We have enormous statistical power when you are able to stack. And because our basically particle background is stable, these stacked observations can reveal this hidden outskirts of clusters of galaxies. And when we stack about 680 massive clusters of galaxies selected in the first eROSITA all-sky survey, we got this beautiful image. So you can see the scales. It's an all-sky survey that has that advantage of large field of view. We here stacked all the massive clusters in the nearby universe. We have collected 3 million source counts. And that adds up to total exposure times solid angle is about 1 million degrees square second. These are basically survey jargon. But if you look at the surface brightness, X-ray surface brightness of these clusters from their center to the outskirts, you will see that we detect cluster emission out to 5 megaparsec, right? So this is way beyond what is available right now. So Russian team actually did this similar stacking in the eastern galactic half, but they only stacked 38 clusters, which are shown in blue here. So they don't really go far beyond virial radius. So we can detect the basic cluster gas, or what you call it, CGM, out to R200M. So the question is then, if we can model the inner radius with the models we know of, we can, or generalize NFW profiles, how about the outskirts? Basically, these models are not suitable for modeling that emission, which comes from filaments and infalling halos. To model that emission, we actually go beyond what has been provided in the literature, and we use matter-matter correlation function, assuming some halo mass function and scaling relations. And what we find, in fact, is that 50% of that gas is in filamentary plasma, and remaining 43% is in infalling halos. This is and now we can basically successfully fit that excess emission in cluster outskirts for the first time. But you can take this a little further. So, okay, we went out to 5 megaparsec. We could characterize that gas now, but there are a lot more baryons in the universe. Actually, majority of baryons are in this cosmic web, what you see here in the blue map. These blue, basically vein-like structures are SDSS identified filaments. So they are optically identified through their galaxy emission. And we projected those filamentary catalogs on the eROSITA sky and stacked about 8,000 filaments. So these are really large structures. Their physical length ranges from 20 to 100 megaparsec. They are cosmic filaments. So they are basically, the baryons here are so faint that you would not be able to observe with individual observations. But here, what we do is we stack, of course, that increase our statistical ability to detect these features. When we look at the X-ray emission from this should be okay. X-ray emission from their center to the outskirts. We detect this gas with 9 sigma significance. But of course, there are a lot of emission that we do not detect, which are beyond our detection limit. If we model those using our eROSITA twin simulations, we can basically find that 5.4 sigma of those that gas is coming for the CGM from the filament. What we also find through our spectral stacking, this temperature is about 0.5 keV. And if you assume some geometry, our local overdensity is 30 to 100, and we can account for 20% of the missing baryons in these filaments. So these are all consistent with the simulations. On the left-hand side, you see the phase diagram coming from illustrious simulations. On the y-axis, that's the temperature in filaments. On the x-axis, the baryonic overdensity. And you can see this gas mostly would emit in the UV, but in the X-rays with eROSITA, we see the tip of the iceberg because the hottest gas would emit in the X-ray band. So these all make sense. So that's all I wanted to say. The first part of this presentation actually has not been submitted yet. So you are the first people to see those results. But eROSITA gives us enormous statistical power to stack observations and probe the faintest baryons in the universe. But when you stack, you average, right? So you lose the information in individual objects. What Axis would provide us the sensitivity and the resolution to look at the individual objects out to the large radius. Then we will be able to actually, with Axis observations, without averaging, with direct imaging of the infalling halos in the cluster outskirts and filaments, we can understand the structure formation a little better. Thank you very much. I'll stop here.
Okay, we have time for a few questions, if we have any. Okay. Yep, good.
That was really cool, Esra. The 2 halo term stuff, did you mask all detected X-ray sources before stacking, I assume?
Yeah, actually, that's a very good point. We remove all the emission that we detect. So we have source catalogs, right? AGN and cluster source catalogs, we remove them. But we also remove everything optically identified up to now. So whatever optical catalog, we collect and remove those objects as well.
Okay.
Yeah.
Cool.
We are very careful.
Yeah, no, that's really so because usually when you talk about the 2 halo term, it's a clustering analysis type thing, right? But you've removed the things that cluster, which is halos, and so this is really, you know, I wouldn't call it a 2 halo thing. I'd call it like a supercluster or protocluster web that you've detected, I think. Yeah.
Yes, exactly, exactly. So the weak lensing people or optical people use that 2 halo term. So we were not sure, we are still not sure what to call it. But yeah, we are seeing basically much diffuse plasma than that they would see.
Okay.
Thanks, Esra. This is super cool. I'm wondering whether or not when you have the map of the filaments on top of the clusters, are the filaments, the optical filaments, well identified enough that you could actually stack, do the thing that you did in the simulation and stack along the filaments and then away or then in toward the voids, but starting on each cluster? Do you see what I mean?
Yeah, yeah. Actually, this is one of the things that we want to do. But you see here, the problem is we only have half of the survey. So although like there are not really a lot of statistical power that we can play that game, unfortunately. Maybe if we had the entire hemisphere or twice as much as data, we could have done it.
Right.
Yeah, but it's a hard measurement to make.
So I'm intrigued by the temperature you're getting. I remember there were two Suzaku quote unquote filaments, say Bell 399, 401, and I forgot what the other one was. And they were finding temperatures like 200 electron volts, which was terrible because that's the same temperature as the diffuse gas in the Milky Way. And so you have this tremendous projection problem. If I'm assuming your results are correct, that makes it much easier for AXIS to see this stuff literally, because it's 2.5 times hotter. Is that a bit of a surprise, the temperature you're getting?
Yeah, it's still puzzling me why this temperature is so hot. But to be honest, when there is another group in Bonn, we independently work and they look at the individual filaments, they see similar temperatures, and we see similar temperatures here, hot temperatures. I don't know why this temperature is really warm, but if it is really warm and these results are confirmed by, for example, hopefully when CRISM opens its gate valve and looks at these observations, looks at these binary clusters in deep observations and confirm the temperatures, then definitely AXIS could see them without much effort.
Yeah.
Yeah, I'm really hoping these results actually will be guiding for AXIS simulations in the future.
Half a keV is a really nice temperature because you get the oxygen, the helium-like the hydrogen-like oxygen lines.
Yeah, absolutely. Yes. And some of this gas, I mean, you see in the simulation, some of this gas is definitely hot, right? But not most of it.
Okay. Thank you, Esra. Our next speaker is Anthony Flores.
To the beginning.
Oh, yeah. I know. It's always beginning. Okay, next we have Anthony Flores with a revolution in high-redshift galaxy cluster science with AXIS.
Okay, thank you. Everyone can hear me? Good. Okay, I'm Anthony. I'm a graduate student at Stanford. I'm excited to be here today to tell you about my work in the current and hopefully next generation focusing on high redshift clusters. I'll also say this is not my first time being immediately preceded by Esra in a talk, so thank you very much for giving that intro, particularly for cluster outskirts. My primer on clusters, I usually like to show this image of El Gordo at a redshift of just under 0.9 because it's one of the most massive of the most massive objects in the universe. You can pick out the BCG in the lower left-hand side of the system. Depending on what side of the room you're on, you might be able to pick out the gravitational lensing arcs from the absolutely massive dark matter halos. But I especially like this image because it was very easy to overlay the Chandra image, which reveals the intracluster medium, the exceptionally diffuse, incredibly hot plasma permeating this object. That is a significant amount of the total cluster mass and almost all of the baryonic mass within these systems. And just by comparing the X-ray and infrared images, you can much more cleanly resolve the total internal structure and even dynamic and morphological history of these systems. For example, looking at how the X-ray peak is offset from the position of the BCG, indicating that El Gordo has been growing through a series of violent major mergers. But for the rest of this talk, as through most of my PhD, I'm going to ignore almost everything except for the intracluster gas. And that's because the hot ICM is the best and most direct probe of the thermodynamic and chemical state of these massive clusters and galaxy groups, having integrated over all of cosmic time. So you can think about how as clusters are growing out of the cosmic web and accreting hot gas, they continuously shape The environments in which their member galaxies are evolving and through the feedback loop are being affected, or their evolution is being affected as well. And so a very natural question is, how do these energetic processes from AGN activity and star formation activity shape the formation and evolution of the most massive structures in the universe? And if we really want to understand the physics of feedback processes on the large scales of cluster environments, we require detailed measurements of the thermodynamics and chemistry of clusters, stretching out to large radius and stretching back to high redshift, particularly into this period of cosmic noon, where empirically we see the peak of both star formation and black hole accretion processes. One of the example of feedback processes and its effect on clusters that I'm interested in is just the growth of structure itself. So in the canonical model of hierarchical structure formation, if you just had a large, massive dark matter halo and hot gas particles being accreted, one galaxy clusters would be very boring, but they would also grow very self-similarly. There would be a strong universality in, for example, the profiles of gas density once you account for evolution in redshift. But feedback processes disrupt this scale-free evolution, particularly near the cluster core, where you can have, for example, winds, shocked jets that we heard about earlier today, disrupting the infall of hot gas. You can have interplay with cooling flows as the hot gas radiates and cools down and condenses towards the center. This will also disrupt these scale-free, self-similar evolutionary processes. And clusters are also not isolated systems as they collide with other systems in major and minor mergers. You have the dynamical friction of galaxies within as their gas is being stripped. This can all also affect these processes. Another feedback evolutionary question I'm particularly interested in is when and how the universe was enriched with heavy metals. In the lower left here, I'm showing large radius ICM metallicity measurements from the Perseus cluster outside of the cluster core in 8 different directions, showing that the metallicity is consistent with a value of about 0.3 solar. And not only is this metallicity constant within Perseus in multiple different directions, as I'm showing in the right, this is also a universal property of clusters in the local universe, that at large radius, we continue to see this remarkably constant metal enrichment. And if we turn to cosmological simulations to explore this, we find that the only way to reproduce these observations in the local universe is to crank up the AGN feedback to a high degree in order to get these profiles to flatten out. Just accounting for the cumulative effects of stellar feedback, we cannot. But another consequence of turning up the AGN feedback is that you also have to start it very early. And so a natural consequence of this is that you should not only see this enrichment at large radius in the local universe, but you should also see it in the high redshift universe. And this is what we call the early enrichment scenario, where star formation processes enriched local environments. AGN activity expelled the hot enriched gas to very large spatial scales, and then all this matter accreted back onto the host clusters as they grew. In order to test that, you would really like to have measurements of the ICM within clusters at large spatial scale and at high redshift. But that's very much more easily said than done. So what I'm showing here is ACT 0123, a redshift 1.5 relaxed cool core cluster that has about 50 kiloseconds of Chandra data and about a quarter of that in XMM. These are 2 arc-minute aside image cutouts. And if you did not have a trained eye looking at the full field of view, you might even have just trouble picking out the cluster in Chandra. Whereas in XMM, the little red X's denoting a nearby point source, you would not be able to determine the morphology and dynamics of this system. You might think it's a merging system or something that's morphologically disturbed. You wouldn't know it as a cool core plus AGN simply because of the large PSF. So earlier today, there was an exchange between Ryan and Kim during one of the legacy talks of what kind of scenarios would you like high sensitivity and high spatial resolution? And a theme of all of my work is the same answer that Kim gave. It's galaxy clusters. So only by having both the high spatial resolution and the high sensitivity observations are we actually able to make headway into these types of measurements. In particular, if we get shallow Chandra observations to very well constrain the morphology of systems, identify, localize, characterize contaminating point sources, and then forward model that into various XMM analyses that actually have the deep observations and statistics we need, can we actually make progress? And we've done that in a few avenues. Showing here are scaled thermodynamic or density profiles for 10 high redshift clusters above a Z of 1, as well as in the bottom panel, the intrinsic scatter in those profiles as a function of radius. And even out to these high redshifts 1 to 1.7, we're still seeing dramatically low scatter, indicating high self-similarity in cluster evolution. So despite any individually violent feedback processes within specific clusters, this is averaging out over the large scale of these large volumes of clusters. And so we are still seeing this remarkable uniformity in the structure and evolution of the universe. We can also apply these techniques towards metallicity measurements. So as we continually add higher and higher redshift data points, we can get an idea of how the chemical enrichment at large scales is evolving over time. And now with the highest redshift points we've been able to constrain metallicity at large radius for, we're just beginning to see hints of decrease in this constant value out towards a redshift of about 2. So this is preliminary, or in the sense of we still don't have great statistics. We're less than 1 sigma inconsistent with a completely flat metallicity value out towards Z of 1.7. So we still believe that the gas was significantly enriched, stretching back to cosmic noon. Ideally, we would like to have an instrument that has the spatial resolution and the sensitivity to extend these measurements out even further, and that's where AXIS comes into play. So in the lower left here, I'm showing an example from XMM Newton for a redshift 1.3 cluster, indicating that even at very deep observation, once we hit about 10% of net cluster signal to total background components, we completely lose the ability to constrain any cluster parameters. And for this system, that's happening in about 1.5 R500. So typically in the current generation, we can go R500, R200, and then not be able to constrain really anything. We've simulated cluster environments as we would see in AXIS, and we will be able to get out to at least R200 by redshifts of 3 and potentially even further. So AXIS is going to push us out, at least in imaging studies, to the virial radius or beyond, to the highest redshifts that we've ever considered. We've also taken those same observations and simulated spectra for these cluster environments. And so you can ask the question, instead of 100 kiloseconds of Chandra and 100 kiloseconds of XMM, what if I just had 100 kiloseconds of AXIS? And one, there is that huge increase in statistics that we're used to, but because of the high spatial resolution of AXIS, as shown in the lower left here, you'll fully be able to resolve any structure within the cores of these systems that's completely hidden from us now, even in deep XMM observations, simply because of the limited spatial resolution. I've also simulated in this system a metallicity gradient that could help us with indications of actually models of cluster enrichment and its evolution. And again, we'll be able to get good constraints on the metallicity, stretching out all the way to the virial radius, or hopefully beyond, though probably not at a redshift of 3. And this is, at least in terms of statistics, as good as or better than 10 times deeper campaign with XMM Newton. And so this will really transform this space. Focusing even more specifically on metallicity evolution, I said that's a question I'm particularly interested in. It's also a question that the community is interested in. This is a key AXIS science driver. And so using the PI guaranteed time, we will use a few megaseconds to observe a couple of dozen clusters spread between redshifts 1 and 3 to get actually individually constraining measures of metallicity out towards or through the period of cosmic noon. And so what I'm showing here in blue is existing data, existing metallicity constraints, again, barely showing any indication for evolution in metallicity out towards the highest redshifts. But with Axis, as shown here in the red, we will get great constraints individually for metallicity in high redshift clusters, which will allow us to measure the intrinsic scatter in metallicity out towards high Z at large R, see how that scatter may evolve over time if it does. And we will also be able to not just detect this decrease in metallicity, we'll begin to be able to describe how this metallicity is changing or discriminate between actual models of chemical enrichment in the early universe. So we're very excited to do this over the course of the Axis mission to really nail down specifics about the early enrichment scenario. And so I'll end there and throw out my conclusions, but in order to make advances in this space, we really need spatially resolved, highly sensitive measurements of the intercluster medium, which we're currently able to do just in the current generation with the combination of Chandra and XMM, but Axis is really going to advance this space further. So thank you very much and happy to take questions.
Okay, questions? We have some time, so yep.
So I'm going to ask a question that's been asked of a few people, and that is, I know the sensitivity will help you, but is it just the sensitivity or also the extra low energy sensitivity that's going to be helping you? I think it's both.
Oh, yes, absolutely. So especially as there was a science case talked about this yesterday, I think in Asia's talk about the metal lines being shifted even closer to where the higher sensitivities are. So yes, absolutely. The softband sensitivity is absolutely critical to make a number of these measurements, especially extending up to high redshifts.
More questions? I had a question about these cores that you'll see this. You had a plot where you can see the data points kind of heading down. Yeah, here on the left. So this is something you expect to see out to quite high redshifts. Is that my correct understanding?
To an extent. So if I've simulated here a dynamically relaxed, like cool core cluster. So the cluster has time to grow and accrete. There hasn't been a major merger that has disrupted this gas. And so we expect in that scenario, the gas to become incredibly peaked. And then those high densities will force quite a bit of cooling, which will give you this cool core structure. We do expect to identify quite a few of these clusters out to large redshift, but obviously, it takes time for this to form. So looking at the evolution of cool core fractions in the cluster population out to the highest Zs is also something that's going to be...
That's been one of the big questions.
Yeah, so that's going to be really interesting to us. It's not a particular focus of the metallicity measurements, but we are going to focus on the most geometrically simplistic systems in order to get the best modeling. And so it's something that between that and various geo programs we'll definitely be looking to probe.
Yeah, it's super cool.
Yeah.
Very nice. Okay. Did you have a question? Yep.
Thanks for this. It's really interesting. I'm wondering whether Esra just showed us what you can do with stacking the profiles of clusters that are relatively nearby. For higher redshift systems, I imagine there will be a lot of things that could be identified, for example, by the presence of a BCG and a radio source, where you might say, oh, there's a cluster there, but that we don't have enough photons to do a metallicity measurement of just that. Is there any possibility of using other tracers to find the clusters and then stacking them to get some integrated, average metallicity?
Yeah, I haven't thought much about actually stacking the observations that we find. We'll mostly just be looking for a mean anyway, even if we can't constrain the individual scatter, especially out, say, of Z of 3. But in terms of identifying these clusters, so we don't have an exact target list next, but mostly between the SZ, IR, and optical surveys coming up over the next couple of years and decades. So ACT, Simons, Euclid, Roman, LSST, Rubin, that will provide a lot of the cross-matching that will allow us to identify these samples out towards Z of 3 when one observatory alone might not cut it. So that's absolutely going to be how we're identifying these targets. And then if anything, any auxiliary information can be used to help in the modeling, we'll absolutely take advantage of that.
Okay, I think it's time for the last talk of this session, and then you will be allowed to get coffee. So, Erin Boettcher is next, I believe. There you are. Okay.
Oh, that's okay.
Yeah, pull up here. Okay, and so we have Erin Boettcher giving us a talk on Axis and NewAthena and their synergies, which is just great. Thanks.
Thank you. Well, hi, everyone. I'm Erin Boettcher. I'm a research scientist at University of Maryland and NASA Goddard. And I'll be talking about some of the reasons that I'm excited for Axis, and particularly synergies between Axis and NewAthena for starburst wind science in the 2030s. So we've seen that one of the pillars of Axis science is better understanding how mass and metals circulate between galaxies and their ecosystems. And the role of supernovae, and particularly correlated supernovae and stellar winds in the starburst environments of nearby galaxies is a key piece of this. So we see in nearby starbursts these truly spectacular outflows of both hot gas as well as entrained multi-phase cooler gas in galaxies like M82 and NGC 253. And we've had now a number of decades of modeling these winds, and particularly the hot phases of these winds, to try to understand their physics. We know that the hot phase of these winds is particularly important both for driving the wind as well as for transporting the majority of the new metals out of the galaxies, as well as transporting significant energy. But at the same time, we still have a number of open questions about the hot phase of the wind. And this is largely tied to the fact that we don't know directly the wind velocities. Because of this, we don't have direct constraints on the outflow rate of mass and energy from the galaxies. And due to that, we don't know directly, where we don't have direct constraints on thermal gas pressure driven winds versus other potential driving mechanisms such as cosmic ray pressure. So to test these models, what we need are high energy resolution measurements, particularly measurements of the kinematics, as well as precise measurements of temperature and the normalization or line fluxes. But critically, to interpret those measurements, we also need high angular resolution measurements. And this will allow us to infer the densities, masses, and energies, and the outflow rates of those quantities. So in the 2030s, we'll have access to provide those high angular resolution measurements at the same time that NewAthena and the XIFU instrument will be coming online to provide those high energy resolution measurements. In the 2020s, currently, we're getting a first glimpse of what this kind of synergy might look like with a combination of CRISM and Chandra data. So I'm going to start by giving a case study of work done by the M82 CRISM target team of observations that combine Chandra and CRISM analysis to study the hot wind in the prototypical starburst galaxy M82 to illustrate the types of synergies that we may expect from Axis and NewAthena. So starting here, showing the Chandra image of the outflow in M82, we see that there's very complex structure in the wind cone, as well as complex structure from the point sources in the galaxy that create this sort of clumpy appearance in the middle. And this is showing the multi-wavelength image to orient you to the location of the disk. So stepping now to energies that CRISM can access, here I'm showing the silicon-14 2 keV line, the CRISM bandpass being about 2 to 10 keV. We can still see this quite detailed structure. And if we overlay the CRISM resolve field of view, resolve being the microcalorimeter that's providing us with about 5 eV energy resolution, you can see that there's quite detailed wind structure within a single CRISM pixel, as well as a single CRISM spatial resolution element. So here I'm approximating the resolved PSF with the half power diameter shown here. And we see this quite detailed structure within each pixel evolves as a function of wavelength. So here we've gone to the higher energy band. This is the iron 25 6.7 keV shown in the contours here. And you can see that this gas traces the hot thermalization zone, where the supernovae and stellar winds are actively thermalizing their energy in the fluid that is presumably driving the wind. So what we'd like to know is what are the mass and energy outflow rates from that thermalization zone. And the way that we're going to go about determining that is by using Chandra to constrain the wind geometry, so the volume and the surface area, the phase structure, as well as contribution from point sources. And then we'll pair that with CRISM observations that tell us both about the wind kinematics, as well as precise temperatures and line fluxes. And then jointly, that tells us about the density and mass of the wind, as well as the energy and the outflow rates of both of those quantities. So starting with what we can learn from CRISM, we can see here, again, the iron 25 emission seen by Chandra. And what we'd like to know is the volume of the thermalization zone that that gas occupies in order to ultimately infer its density and mass. And we're able to combine the surface brightness profiles from Chandra with multi-wavelength data to infer the cartoon picture on the right, which shows this ellipsoidal region that's contained by a molecular torus. And this is the region in which the thermalization of the star formation energy injection is happening. Now we can also infer the surface area of the outflow, particularly the nozzling of the hot wind by the molecular torus. And this informs the outflow rates of the gas and the mass and metals carried by that gas. We also can infer from Chandra how the various lines that we see in CRISM arise and on what spatial scales. So here I'm bringing in the CRISM resolve spectrum. And you can see at the lower energy portion of the spectrum, tracers like the sulfur 15 line are seen on relatively excited spatial scales, about 1 kiloparsec, in contrast to the iron 25 that we saw previously, which is concentrated in the inner few hundred parsecs. We also see, as you can see on the right, point sources have been removed from these images in order to identify the diffuse emission. And this point source identification is critical both to be able to isolate that diffuse signal and also to better constrain the contribution of those X-ray binaries to the power law that contributes to the continuum of the spectrum. So you can see here that we model this in the CRISM spectrum, but being able to separately extract that point source spectrum and model it in Chandra data helps to constrain that model and to better isolate the thermal continuum. So now moving to the CRISM measurements. This is, again, the resolved spectrum, as well as a zoom in on the iron 25 emission line. And we model this as a 2-temperature model, where it's 2 components in CIE that are also velocity broadened. And we, again, include this power law for XRBs. And we find that the iron 25 bearing gas traces a hot wind, about 2 keV, and that this wind is fast, about 600 kilometers per second line of sight velocity dispersion. And this gives us approximately a lower limit on the outflow velocity of the wind. We also see that that more extended nebula that we see in CRISM does in fact come from gas that's cooler and considerably slower by a factor of about 3. So we can now put these pieces together to infer both the density, mass, and energy and their outflow rates in the thermalization zone. So this yields a mass outflow rate of about 4 solar masses per year, as well as an energy outflow rate that we can compare to the energy injection rate from star formation to yield a thermalization efficiency for the starburst. And we find that this implies a relatively efficient starburst, so about 60% thermalization efficiency, comparing the total power. This is both the thermal and critically the kinetic power, which we can measure for the first time. We find that the thermal power does indeed dominate by a factor of about 3. Finally, we can then ask, given the total power available in the hot wind fluid, how does this compare to the power required by the multi-phase gas to drive the total wind mass that we see escaping from the galaxy or escaping into the CGM? So from literature measurements of the molecular gas, neutral, warm ionized, and soft X-ray winds, we're able to quantify a total power requirement of the cool phase, which does have large uncertainty, primarily due to the wind geometry. You can see that shown here for each phase. But we do indeed find that the power available from the hot wind fluid does indeed meet the requirement of the cool wind. So this suggests that MED2 is well described by a classic thermal pressure-driven wind model. And we don't see evidence that a supplemental source of driving, such as cosmic ray pressure, is required. So I've hoped that showing this case study of MED2 illustrates why we really need this pairing of the high energy and high angular resolution observations to truly make progress on this question of starburst wind driving. So now I'd like to talk about synergies between AXIS and NewAthena as far as taking this kind of science into the next decade. So here I'm showing a simulated image of, again, MED2 from AXIS, and you can see in only 100 kiloseconds that we get this deep, beautiful image of the biconical outflow, where you can see quite detailed structure on quite large scales. So simultaneously, or in the same decade as AXIS is obtaining these beautiful, deep images, we're also going to have NewAthena and the XIFU instrument coming online. So this is led by the contributors listed here. And the XIFU will provide energy resolution of better than 4 eV across a 4-arc-minute field of view, sampled by about 1,500 pixels. This is planned for launch in 2037. So currently I'm working on a feasibility study for essentially quantifying how well we'll be able to constrain hot wind models using the reformulated NewAthena and the XIFU instrument. And the goal here is to develop realistic simulations of starburst galaxies and their environments, and construct mock XIFU observations, and then analyze those observations to determine the types of precision that we can get on key measurements like the temperature, velocity dispersion, and density, in order to compare to predictions from starburst wind models. So I'll just briefly say that to construct these models, we go through a process of, as I said, constructing expected inputs from all emitting components in the galaxy. So in addition to the wind, which we model using either an analytic wind model or directly from Chandra data and measurements extracted from these data, we also include models for the hot ISM and CGM and X-ray binaries in order to fully account for various sources of noise in the spectrum. So just briefly here, we use the 60 suite of the 60 simulation suite to construct mock XIFU observations. And we're then able to, and these are the inputs that go into these observations. So this is a mock of, again, MED2, where you can see, again, the wind cone, as well as the point sources, hot ISM and hot CGM are all included in the model. And then we're able to observe that and generate these mocks. This is showing here the mock image and spectrum, again, of MED2. And you can see here, again, in just 100 kiloseconds, very rich line structure that we're able to detect. This here is the integrated spectrum across that full 4-arc-minute field of view centered on the galaxy. And again, we break that down into the various emitting components in order to understand what energies, what we might expect various components of the signal to come from. So as we saw with CRISM and Chandra, with NewAthena and AXIS, the deeps, the high sensitivity for these missions in particular is going to enable extraction and analysis of spectra from very small apertures across the face of these nearest starburst galaxies. You can see here mock XIFU spectra of several apertures placed along the minor axis or approximate minor axis for M82. And you can see that, again, in modest exposure times, we can go quite deep, both far from galaxy disks, as well as within the disk to truly trace out variation in these fundamental properties of the wind. But due to the, again, larger PSF of the microcalorimeter, or of the mirror paired with the microcalorimeter, in order to interpret what's giving rise to the signal within each of those pixels, we need to be able to go sensitive as well as sharp within each of those apertures to understand what is giving rise to that signal. So I think I'm at my time, so I will say we are currently seeing hints of what we can do by pairing this high angular and energy resolution observations with Prism and Chandra. And we look forward to carrying this into the next decade with Axis and NewAthena. Thank you.
Questions? Okay. All right.
Several questions. So if I remember, M82 is a low mass galaxy, and 460 kilometers a second is greater than the escape speed. Is that correct?
That's right. Yes.
So actually, so how does that compare with like the H alpha velocities?
Yeah. So the deprojected H alpha velocity does peak around 500 to 600 kilometers per second. So there does appear to be at least some cool gas that is also on an escape route.
So if I can force an interpretation upon you, you're basically verifying that all the phases of the wind are basically able to escape the potential well of the galaxy.
So I don't think that that's quite the case, because a lot of the mass is in the molecular phase and that velocity appears to be lower. I think it's challenging because of the need to deproject the velocities in all of these cases. So when we do this power requirement budget for the cool phases, we're making some assumptions about the deprojection, and to the extent that those are correct, the molecular gas is primarily below the escape velocity. So
okay,
I think it's a complex story as far as what's escaping and what isn't.
So two more questions.
Yeah.
What is the abundances of the relative elements with respect to solar?
So we would like to measure that, and that is a next goal for our target team.
And knowing what you know about M82, how many more starburst galaxies can you do with Prism?
So with the gate valve closed, as far as pure starbursts go, like no major AGN contribution, it's really only 253. So we have quite a small sample. With the gate valve open, that's larger by a factor of a few. Yeah.
Okay. Thank you.
Okay. Yeah, I think you want to.
Yeah, so maybe we'll take a
Yeah, let's thank all the speakers from this session.